Welcome to lecture number 13 of matrices. So we will start from here as already told to you in the previous lecture. If A and B are two symmetric matrices. So there are two symmetric matrices A and B, and if they have the same order, okay, of the same order. Now why of the same order? Of the same order because we have to prove that this particular thing. So the addition will be possible only when there will be same order. Addition will not be possible without same order. That's why we are taking same order. Okay. So A and B are two symmetric matrices, and of the same order. For addition to be possible, they are of the same order, and they are two symmetric matrices. Capital A, capital B. Okay. Then what does the property say? The property says that λ₁A plus λ₂B is also symmetric matrix for any scalars λ₁ and λ₂. Now whenever we talk about scalars in matrices, it simply means constant. Scalars means constants. Okay. What does it mean by scalars? Scalars means constants. Okay. So they are of the same order, they are symmetric also, and this particular expression λ₁A plus, okay, over here it is plus, okay, λ₁A plus λ₂B, λ₁A plus λ₂B is also symmetric matrix. We have to show that it is also symmetric for any scalars λ₁ and λ₂, which are constants. So it is also symmetric. We need to show this. This is the property. So how to prove it? Capital A and capital B be two symmetric matrices as already given to us in the question itself. A and B are two symmetric matrices. So as A and B are symmetric, A transpose will be equal to capital A, capital A transpose will be equal to capital A, and capital B transpose is equal to capital B. Why? Because they are symmetric, and whenever a matrix is symmetric, this particular condition is satisfied. Okay, this particular condition is satisfied whenever a matrix is symmetric, and A and B both are symmetric. So this particular condition will be satisfied by these matrices A and B. This particular condition will be satisfied. Let us name this as equation 1. Okay, so this is equation 1. Now TS means to show. So this TS, what does it mean? It means to show. To show λ₁A plus λ₂B is symmetric matrix. We have to show this. So whenever you solve any problem, any proof type of problem, to prove problem, if you solve any to prove problem in mathematics, what are the first steps? The very first step is that you have to write the given information. Okay, very first step is you have to write the given information, and after that you have to write to show what you need to show, and then we move on towards the proof. After that, after we write what to show, we move on towards the proof. Okay, so to show that this particular thing is symmetric matrix, now that is to show that λ₁A plus λ₂B whole transpose is equal to λ₁A plus λ₂B. Now we have to show that this is symmetric, so this condition must be satisfied by this as well. This particular condition, if it is satisfied by symmetric matrices, and we have to show that this is symmetric matrix, then this particular condition must also be satisfied by this expression. It must also be satisfied by this. So if we want to show it is symmetric, we need to show that its transpose is equal to that matrix itself. Okay, its transpose. Okay, this is complete one matrix now. This is complete one matrix. You can name it capital C. This is complete one matrix, and you can name it capital C. So capital C transpose is equal to C. Okay, capital C transpose is equal to C. So you have to prove this. Okay, you need not write it as C. I showed you as C for convenience, but you need not show with the letter C. You need not show. I showed it to you for convenience. Okay. So how to prove them? So we will start with this particular thing, and we will obtain this. We will start with this, and we will obtain this. Okay. So how to obtain? Let us see. λ₁A plus λ₂B whole transpose is equal to λ₁A plus λ₂B whole transpose is equal to λ₁A transpose, λ₁A whole transpose plus λ₂B whole transpose. Now, how did this happen? This happened because of this particular property. A plus B whole transpose is equal to A transpose plus B transpose. Okay. Now in the place of A we have λ₁A. In the place of B we have λ₂B. Okay. So just substitute in the place of A λ₁A and at the place of B λ₂B. So this is the final expression. This expression will be equal to this particular expression because of this particular property which I have taught to you in the previous lectures. Okay, I have already taught it to you. Now we will use one more property, that whenever a scalar is multiplied to a matrix, and you are taking its transpose, that is, whenever a scalar lambda is multiplied to a matrix and you are taking its transpose, the constant can be taken out. And simply A transpose can be written. So λ₁A whole transpose is equal to lambda A transpose. Okay. And lambda is a scalar here, that is a constant, so constant can be taken out. So λ₁A whole transpose is equal to lambda A transpose. Okay, so λ₁A whole transpose, in the place of lambda we have λ₁, so λ₁ can be taken out because it is a scalar or constant. So λ₁ A transpose, and this can be written as λ₂B transpose. Okay, using this particular property. Okay, and you have to put 3 dots here. You have to put 3 dots like this. Okay, you have to put 3 dots like this. Okay, over here. Okay, since this symbol means since. Okay, this is the mathematical symbol for since. Okay, this is the mathematical symbol for since. So up to here it is clear. Now what to do? Now you already know from this equation 1. You already know that this A transpose is equal to A itself because it is symmetric, and this B transpose is equal to this B itself because it is symmetric. So just substitute in the place of A transpose you will substitute A, in the place of B transpose you will substitute B. So by equation 1 means by this particular equation. Okay, so by equation 1 you showed this. A transpose was A, so you replaced it with A, and B transpose was B, so you replaced it with B. Now have a look at this particular fact. Now have a look at this particular expression. After you look at this particular expression, you can certainly say that this particular thing is a symmetric matrix. Only then, if this condition holds good, this is the conclusion. Okay, if this particular condition holds good, then this is the conclusion. Okay, and what is the conclusion? λ₁A plus λ₂B is a symmetric matrix. So we have successfully showed that λ₁A plus λ₂B is a symmetric matrix, successfully showed. Okay, from here onwards we will move in the next class. Hopefully it is clear to you. Okay, so λ₁A plus λ₂B is a symmetric matrix. So we have successfully proved that if A and B are two symmetric matrices, then λ₁A plus λ₂B will also be a symmetric matrix where λ₁ and λ₂ are any two scalars. Okay, from fifth property onwards we will move on in the next class. Okay, thank you very much.